In this lesson, we'll do a quick review of what vectors are in two-dimensional form, and then we'll look at conversions from component form to polar form. So a vector can be represented in one of two ways. Initially, it will have a direction and a magnitude we refer to as polar form. It can also be a relationship in space of one point relative to another, and that will be referred to as component form. Now these are the same thing, they're just different representations of the same thing. So if I was to draw a vector between an origin point O and point A, then this can be represented by the vector AB, or we could also give it a name, a direction vector A. The polar form of this can be represented by the angle from the horizontal and then the magnitude of this vector A. So this is the magnitude of the length, and that can be represented by the modulus symbol around A. Okay, so that's polar form. Vector A is the magnitude and direction. Now, when we think about this in component form, what we're worried about is the displacement in the x and y direction. So here's our displacement in x and our displacement in the y direction. And so in component form, we get A is equal to x in the I direction and displacement y in the j direction. This can also be written as a storage vector. A is equal to x, y. All right, so what we're doing today, and the focus of this lesson, is to convert between component and polar. So from component to polar form. That means we need to take what we have here, and we need to be able to calculate that magnitude and direction. Okay, so this will be nice and simple. The magnitude can be calculated using Pythagoras' theorem because these are perpendicular displacements. So essentially we're looking at the magnitude squared is equal to x squared plus y squared. When we rearrange and isolate for the magnitude, we end up with square root of x squared plus y squared. Okay, so calculating the magnitude is as simple as that. The direction can be a little bit more complex because it is dependent in which quadrant it falls in. The domain for the direction will be between 0 and 360 degrees. And obviously, as it extends beyond 360 degrees, we'll get coterminal angles. So we always start 0 degrees from the right-hand x-axis, and then we rotate counterclockwise. Right? So if we're in this quadrant, then the angle is whatever we calculate. If we're in quadrant 2, so we'll call this one quadrant 1. If we're in quadrant 2, then the angle will be, because we'll calculate the acute angle, will be 180 degrees, take away the calculated acute angle. If we're in quadrant 3, the angle will be 180 degrees plus the acute angle. And if we're in quadrant 4, the angle will be 360 degrees, take away the acute angle. So that's really important because when we calculate the angles, the acute angle, we're always finding these ones. So we're using arctan. So the direction will calculate the acute angle, which will be arctan of the opposite over adjacent, so y on x, and then we'll adjust to find the angle from 0. Okay, so we'll look at a couple of examples here. Okay, in this example, we want to convert -1i plus root 3j to polar. So if we look at that in Cartesian form or component form, -1 in the I direction and root 3 in the j direction, then we end up with a vector in quadrant 2. So this will be alpha. We want to find this angle from the positive I-axis, and we want to find the magnitude. So we'll start by finding the magnitude. Magnitude is square root of 1 squared plus root 3 squared. You'll notice I didn't bother putting the sign in. Obviously, any negative number squared will be positive. So 1 plus 3, square root of 4, we get 2. Now, to calculate alpha arctan of root 3 on 1, so you should be able to recognize these as standard triangle values, and the answer there is 60 degrees. You notice again I didn't put the negatives in. That's because throwing those negatives in will complicate the scenario. If we do it as a positive angle, we know that this angle here is 60 degrees, and therefore the angle that we're looking for will end up being 180 degrees, take 60, and we get 120 degrees. So A is 2, 120 degrees. And that's our vector in polar form. Okay, so in this second example, we're looking at converting vector B, which is 2i take 2j, to polar form. So again, when we visualize this, 2 in the I direction, -2 in the j direction, we end up with a vector in quadrant 4. So this is the alpha that we'll be calculating, which means we'll be looking at the angle is 360 take alpha, or we could just use the angle is negative alpha. I'm going to reduce the space that I calculate this in. So I'm going to say that B is equal to square root of 2 squared plus 2 squared. So that's our magnitude. And I know that it's going to be 360 subtract arctan of 2 on 2 for my angle. So you can see I put it all into the one calculation instead of spreading it out. So I've got square root of 4 plus 4, which is 8. And I've got 360 subtract arctan of 2 on 2 is 45 degrees. So if I simplify this third, I end up with 2 root 2, and 360 take 45 is 315. And there we have it. Vector B in polar form is 2 root 2 and 315 degrees. In this last example, we'll look at converting vector C, which is -4i take 5j to polar form. So again, we visualize this vector, and we've got -4 in the I direction and -5 in the j direction, so we end up with a vector in quadrant 3. This is the angle that we'll find. We'll end up looking at the angle being 180 plus alpha. So vector C will be square root of 4 squared plus 5 squared, and then 180 plus arctan of 5 on 4. So 16 plus 25, so square root of 41, and then 180 degrees plus 51.34 degrees. So you'll have to use your calculator for that one. And that means my vector C in polar form is square root of 41 and 231.34 degrees. There we have it. That's how you convert component form to polar form using 2D vectors.